Hey F1 fanatics, and welcome back. We all love the roar of the engines, the lightning-fast pit stops, and those heart-stopping overtakes that define Formula One. But beneath the glamour and the drama of race day lies a hidden war, a battle of wits and innovation that truly makes F1 the most advanced sport on Earth. This isn't just about who crosses the finish line first. It's about the relentless pursuit of engineering perfection, pushing the boundaries of what's possible. From the earliest days, F1 has been a laboratory for groundbreaking automotive technology, shaping not just racing, but also the cars we drive every day. Today, we are celebrating the unsung heroes, the engineers, the designers, the visionary minds who dared to dream differently. We are counting down the top 5 engineering breakthroughs that didn't just change the game, they created an entirely new one. Get ready to rev your engines, because this countdown is going to blow your mind. Coming in at number 5, it's an innovation that literally changed the fabric of Formula One, the carbon fiber monocoque chassis. Before this, F1 cars were built with aluminum sheet metal, often leading to catastrophic consequences in crashes. Drivers faced extreme danger, and safety was a constant, terrifying concern. But then came a material that would redefine both performance and protection. This was more than just a material swap. It was a paradigm shift in structural engineering. Lotus, under the brilliant mind of Colin Chapman, was at the forefront, but it was McLaren in 1981 with the MP41 that truly launched the carbon fiber era. This revolutionary material offered incredible strength-to-weight ratios, making cars both lighter and immensely stronger. A carbon fiber chassis could absorb massive impact energy, protecting the driver like never before. Suddenly, F1 cars were not just faster, they were significantly safer, turning potential tragedies into survivable incidents. It truly was a game-changer for the sport. The adoption of carbon fiber wasn't just a fleeting trend, it became the industry standard. Every F1 car on the grid today owes its fundamental structure to this material. It allowed designers to create incredibly rigid and aerodynamically efficient vehicles, giving birth to designs that were simply impossible with previous materials. This wasn't just an improvement, it was a complete reimagining of how a race car could be built, proving that engineering ingenuity can literally save lives while pushing speed limits. A true masterpiece of material science. Screaming into number 4, we have the legendary turbocharged engines of the 1980s. Before turbos, naturally aspirated engines were powerful, but there was a ceiling to how much horsepower they could produce. Then, Renault stepped onto the scene in 1977 with a revolutionary, albeit initially fragile, 1.5-litre turbocharged engine. This wasn't just an engine, it was a statement, a declaration that F1 was ready for a new level of power, efficiency, and engineering challenge. It changed everything we thought about F1 power plants. These weren't just turbos, they were beast star. By the mid-80s, these engines were producing incredible amounts of power, often exceeding 1,000 horsepower in qualifying trim from tiny 1.5-litre blocks. Think about that, 1.5 litres, producing more power than many supercars today. This meant mind-bending acceleration and stratospheric top speeds, but also brought immense engineering challenges, managing lag, cooling, and reliability. It was a true test of engine builders' prowess, pushing materials and thermodynamics to their absolute limits. The turbo era was a spectacle of raw power and mechanical ingenuity. While the original turbos were eventually banned due to safety concerns from their extreme speeds and power, the knowledge gained in forced induction, thermal management, and fuel efficiency was invaluable. It laid the groundwork for the hybrid turboelectric engines we see today, proving that even a technology deemed too extreme can contribute profoundly to future advancements. The spirit of those screaming turbos lives on in every modern F1 power unit. Blasting into the number 3 spot, we have an aerodynamic marvel that utterly transformed how F1 cars stuck to the track: ground effect. Forget big wings. Ground effect was about turning the entire car into a giant inverted wing. Pioneered by Colin Chapman and his brilliant team at Lotus in the late 1970s, specifically with the Lotus 78 and 79, this wasn't just about adding downforce. It was a revolutionary approach to aerodynamics that unleashed unprecedented levels of grip, literally sucking cars to the asphalt. The concept was simple yet ingenious. Use venturi tunnels on the underside of the car, sealed by sliding skirts, to accelerate airflow, creating a low-pressure zone beneath the car. This vacuum literally pulled the car into the ground, generating massive amounts of downforce with minimal drag compared to traditional wings. The resulting cornering speeds were insane. Drivers reported an almost otherworldly level of grip, fundamentally changing driving styles and lap times. It was pure aerodynamic wizardry, born from radical thinking. Ground effect cars were so effective, they became dangerously fast, putting immense strain on drivers and their bodies. When the skirts failed or the seal was broken, the loss of downforce could be sudden and catastrophic. The genius of the engineering was undeniable, but its inherent dangers led to its eventual ban in 1983. Yet, the principles of controlling airflow under the car remain crucial today, albeit in a more controlled, regulated form. Ground effect stands as a testament to the sheer audacity of F1 engineering and its pursuit of ultimate performance. Edging out the competition for number 2, it's the legendary active suspension systems of the late 80s and early 90s. While Lotus tinkered with it in the early 80s, it was Williams, with their FW14B in 1992, that truly perfected and weaponized this technology. This wasn't just about springs and dampers anymore. It was about computer-controlled hydraulics constantly adjusting the car's ride height and attitude. It was like giving the car its own brain, allowing it to adapt to every nuance of the track, second by second. Nigel Mansell famously dominated the 1992 season with the FW14B, and active suspension was a massive part of that success. The system allowed the car to maintain an optimal aerodynamic platform at all times, regardless of braking, acceleration, or cornering forces. It removed pitch and roll, keeping the tires in perfect contact with the road and maximizing grip. It was a visible advantage, a car that looked glued to the track, effortlessly navigating bumps and curbs. This was true AI, decades before AI was a mainstream buzzword, working tirelessly for peak performance. The complexity and sophistication of active suspension were staggering, requiring cutting-edge electronics and hydraulic systems. It represented a peak in the integration of software and hardware to achieve dynamic vehicle control. Ultimately, like ground effect, it was deemed too effective and expensive, leading to its ban in 1994, along with other driver aids. But its impact on vehicle dynamics and computer-controlled systems echoed through the automotive world, laying groundwork for stability control and advanced suspension in road cars. It was a masterclass in control, taken to the extreme. And finally, claiming the top spot, the undisputed champion of F1 engineering genius, the hybrid power unit era. Introduced in 2014, these aren't just engines. They are the most efficient, complex, and powerful internal combustion machines ever created. Combining a V6 turbo internal combustion engine with 2 sophisticated electric motor generator units, they harvest energy from both braking and exhaust gases. This isn't just an evolution. It's a revolution in power generation and energy recovery, making them both incredibly potent and remarkably fuel efficient. Think about it. These 1.6-litre V6 engines produce well over 1,000 horsepower, pushing thermal efficiency ratings above 50%, a figure unheard of in production car engines. The MGU-K, kinetic, recovers energy from braking, while the MGU-H, heat, harvests energy from the turbo's exhaust gases, converting waste heat into electrical power. This intricate dance of mechanical and electrical systems means drivers manage not just fuel, but energy flow, creating a complex strategic layer to every race. It's a masterclass in multidisciplinary engineering. The hybrid era demanded an unprecedented level of integration between engine manufacturers, chassis designers, and electronic specialists. It's a testament to F1's continued role as an incubator for automotive technology, with lessons learned in battery management, energy recovery, and high-efficiency powertrains directly influencing the development of future road cars. The brilliance lies not just in their power, but in their incredible sustainability, proving that peak performance and environmental consciousness can indeed go hand in hand. This is truly engineering at its most visionary. So there you have it, our countdown of the top 5 engineering marvels that have shaped Formula One history. From life-saving carbon fiber to the mind-boggling complexity of hybrid powertrains, F1 has always been about pushing the limits of what's technically possible. It's a relentless cycle of innovation, where brilliant minds tirelessly work to gain every millisecond, every ounce of downforce, every drop of power. The legacy of these engineering giants reminds us that the true heart of F1 beats not just on the track, but deep within the blueprints and workshops. Which F1 innovation do you think deserves the top spot? Or did we miss a revolutionary breakthrough that changed the game? Let us know in the comments below. Don't forget to like this video, subscribe for more deep dives into the world of F1, and hit that notification bell so you don't miss our next upload. Until then, keep those engines revving, and we'll see you on the next lap.